Hi, and welcome to another video in this series about Probability Theory, the Logic of Science by Edwin Jaynes. In the last video, we talked about chapter 5 in the book, but for this video, we're actually going to skip ahead a bit and talk about chapter 16, which is Orthodox Methods, the Historical Background. And the reason that I want to take things out of order a little bit is that before we get too much further into the statistical methods that Jaynes is going to lay out in kind of the remainder of his presentation, I think it's helpful to give more of the kind of context to what those ideas are in some way in response to and what Jaynes is reacting to in what he calls the orthodox methods or orthodox statistics. And especially for those of you who may not have seen that standard statistics material, I hope that this will be somewhat helpful in just kind of filling you in and showing the standard presentation and what it is about those methods that Jaynes finds so troubling and why he wants to replace them with his more logically sound approach. Okay, so that's basically going to be this video and the next one. Today, what we'll do is kind of go through the thought process of orthodox statistics and think about where that might work and actually give kind of decent results. And then next time we'll get into the real criticism of it and we'll look at where those methods will break down and kind of where we expect there to be problems. So today I'll do my best to present those fairly, but obviously there's more in the kind of orthodox standard statistics curriculum than I can really present in one video. But at least I think we'll get to the key ideas of the thought process of orthodox statistics. Also, I think it's useful to just give some of the history of where these ideas came from and what problems they were meant to address, and who the people were who did kind of the development of it. So we'll start with a little bit of the history. Jaynes tells this story of statistics in the kind of first half of the 20th century as really being about some major public disagreements and arguments between a few key principal figures. Okay, and the few that we're really going to focus on. First of all, we have Harold Jeffreys, okay, who was a geophysicist, okay, so a physicist interested in earth science, seismology, questions like that, working in Cambridge. And he represents for us the probability as logic, the Bayesian program that the way that Jaynes is trying to lay it out. So he's basically going to be the hero of the story. His disagreements were with, among other people, a guy named R.A. Fisher, okay, who we've mentioned before. Okay, so Ronald Fisher, who was a biologist and actually studied quite a lot of kind of data science questions about population biology and agriculture and genetics and all these kinds of things. So he was a professor at University College London and is most kind of celebrated for or known for a book that he wrote called Statistical Methods for Research Workers. Okay, so just to abbreviate that. Research Workers, and that's 1925. Okay, thereabouts. So he's a very influential person, and this book that he wrote about statistical methods is kind of a standard reference in this area. He, in turn, had some disagreements with some other statisticians, in particular a mathematician named Jerzy Neyman. Okay, so we've mentioned him before. He was a Polish mathematician. He spent a good part of his career at the University of California in Berkeley and very interested in mathematics and statistics. And his collaborators and kind of contemporaries, in particular a guy named Egon Pearson, with whom he developed a very famous theorem called the Neyman-Pearson lemma, or Neyman-Pearson theorem. And Egon's father a guy named Karl Pearson. Okay, also mathematical statistician, and actually Karl Pearson is really the first person who we'd say adopted the label statistician in the way that we kind of now understand it. So he was he founded a department of mathematical statistics, and kind of one of the very first influential people in the field of statistics in the early 20th century. So Pearson and his son, Egon Pearson, together with Neyman, do kind of one program of statistics and statistical inference. Fisher, in his work, develops kind of a different program, and they have many kind of arguments between them about the right ways to do things and kind of the finer details of what they're doing. Really, for Jaynes, the differences between these two schools of thought are not going to matter too much, because as Jaynes is going to lay out, they are all kind of wrong in the same ways. Okay, so basically, Jeffreys is for us going to be what we think of as the Bayesian. Okay, probability as logic, or Jaynes program that we're trying to develop. The rest of these guys together are going to represent orthodoxy. Okay, and in fact, the methods that we kind of use today in statistical practice are basically some hybrid of what Fisher and Neyman and Pearson came up with. Okay, so we're sort of blending their ideas together when we talk about orthodox statistics. Now, Jaynes goes into some of the stories of these people and talks about their personalities. It's pretty clear that he has a strong preference for Jeffreys. Okay, not just because he agrees with him, but also just as a person. He actually, the book is dedicated to Harold Jeffreys. He describes Fisher in some very unflattering ways and says that he, lacked a sense of humor and that he was possessed of a colossal, overbearing ego and things like this. He doesn't talk too much about these guys. Karl Pearson actually just, by the way, was I think a pretty extreme anti-Semite, and someone who his primary interest in statistics was in eugenics and what's called social Darwinism, and the idea that people with superior genetic backgrounds should rise to the tops of society. And one of the big concerns that he had at the time was about the influx of immigration into Britain, especially from Jews in Eastern Europe. Okay, so Poland and Russia and Eastern European Jews coming into Britain, and he had this idea that they were genetically inferior and that therefore would be kind of parasites on the British people. Okay, so one of the things he was actually trying to accomplish with his statistical methods was demonstrating that scientifically, that certain races are kind of genetically inferior to others. Fisher, for his part, spent, I think, a good portion of the latter part of his career basically as a shill for the tobacco industry. He had been a smoker his whole life and then got on board with the tobacco industry and fighting against these studies that showed a correlation between smoking and lung cancer. He basically tried to make the argument that you can't prove from the statistics that smoking causes lung cancer just because there's a correlation. Okay, fair enough, but interesting that he didn't apply that same argument maybe to any other question of statistical inference, just the one that he was kind of biased towards. So anyway, I think that the way Jaynes lays it out, especially, we're supposed to kind of favor Jeffreys in this story, but he does kind of make the points that Fisher and Neyman and Pearson, these guys were all very accomplished mathematicians and statisticians and very influential, and certainly these books, and especially this book of Fisher's, becomes basically the dominant book in this field, and everything that we kind of now understand as statistics in some ways traces back to the influence of one of these people. So they disagreed with each other very, very publicly and very acrimoniously. What is it that they were arguing about? Well, the substance of those disagreements really comes back to this whole kind of question of what is probability and what is the right way to think about scientific inference in the framework of probability. Okay, so in the Orthodox kind of presentation, okay, so we sort of put on our Orthodox statistics hat for a minute and just talk about the ideas of Orthodox statistics. Probability, okay, in that world comes about as a result of basically randomness or chance. Okay, so the idea here, and this really kind of traces back to the earliest gambling game applications of probability, kind of the things we talked about much earlier. The idea is when you do something, say, you have some experiment, or you flip a coin, or roll some dice, or whatever it is, what is going on in the outcome of that experiment is something kind of intrinsically random, right? So you are engaging with a system or a phenomenon that is somehow random or subject to chance, and all you're really doing when you repeat it over and over again is just kind of giving it an opportunity to have different outcomes based on the probabilities that are just sort of inherent to it. Okay, so you can kind of imagine where this would come about. So again, you try to flip a coin. You can't reasonably make the coin come up one way or the other, no matter how hard you try. So you keep flipping it. It keeps coming up heads and tails about half the time each. And so it's natural kind of to conclude that there is something inherently random about that system, and that you are just kind of engaging with that. And that's what probability means in the kind of Orthodox framework. And the way that this will usually kind of get played out in any standard presentation of statistics is it will first define what we think of as the sample space, okay, which is the universe of all possible outcomes of whatever phenomenon or experiment we are conducting. Okay, so just as an early example, what you might see is the example, let's say we flip two coins and we think about the possible outcomes we can get for the two flips. Well, we'd say that we can either get two heads, we can get heads and tails, we can get tails for the first coin and heads for the second one, or we can get two tails. Okay, so that's kind of all of the possible experimental configurations and outcomes of that setup that we can conceive of. Okay, there's then usually some assertion or claim that the way we've designed this sample space makes all of these equally likely, okay, just kind of intrinsically to the experiment, that they all have equal likelihood of occurring. And so then the question about, the probability of some event is basically just going to amount to counting up points in this sample space, or outcomes in this sample space that map onto that event that we're interested in. Okay, so for example, in this case, let's say we want to know what's the probability of getting at least one coin with that comes up heads. Well, we can look at all of our points in our sample space that correspond to that outcome, and say that each one of these has to have probability of fourth because they add up to 1. So that's going to be just, this outcome plus the second outcome plus the third one. Those are the ones that correspond to the event we're interested in, and therefore its probability sort of is 3/4. Okay, and an important thing to note here is that we don't have, the way that we've built it up, we don't have this conditioning information that captures all of this background information or assumptions that we have about the problem. We're just going to assert basically that this is the probability. Okay, so the question then is, okay, how do you come up with this sample space, and how do you know that you did it right and you got kind of possible outcomes that actually were equally likely? And what the Orthodox statistical argument is going to basically consist of is that you can always verify these probabilities just by doing the experiment a large number of times. Okay, so in this case, we'd imagine flipping these two coins over and over again, and looking at the limiting frequencies that we get of each one of these outcomes, possible results of the pair of coins, and we'll say, okay, if it happens that each one comes up about a quarter of the time, then we were correct in our assumption that these were equally likely, and therefore the probabilities we've calculated as a result are correct. Okay, so in the end, fundamentally, probability is going to be about randomness and chance, and we're always going to verify this, or at least be able to verify it by means of looking at limiting frequencies, frequencies of occurrence over a large number of trials. Okay, so in the end then, I mean, after kind of setting it up that way, we'll get to actually the same mathematical rules of probability that we have come to through our understanding of probability as a numerical assignment to plausibility of a statement. Okay, it's just that the rules, things like the sum rule, the product rule, okay, definition of conditional probability, etc., those rules are just going to basically amount to manipulating these frequencies or these proportions of subsets of the sample space. Okay, but this is kind of, I think, where part of the confusion has the opportunity to come from, that the rules of calculating things like relative proportions are the same as the rules that we've come up with for conditional plausibilities and probability as logic. All right, so because we have the same mathematical framework, there's going to be a lot of natural kind of overlap and collision between the ways that we just write out equations and things. Okay, so the question then is, or maybe the kind of extension of this is to say, all right, what gets a probability? So what is random? I guess is the way to ask that question. Okay, so in the Orthodox framework, right, where probability comes from chance occurrence or randomness in some physical experiment and can be measured by frequencies, one of the things that this means is that we're limited to only talking about probabilities for things that can vary in a randomized experiment. Okay, so in essence, we'll say only the data is random in the Orthodox presentation. Okay, now again, for us, we are able to associate probabilities to any kind of statement or proposition, but in this framework where probability is supposed to mean something you can verify experimentally or has to do with chance variation, what it means is that only things like the data and the properties of the data are subject to randomness and therefore get probability assignments to them. Okay, so Jaynes makes the point here that it's a bit strange that you would think that the data, which is kind of usually the only thing that you have for sure in an experiment, that is the thing that is treated as random or gets a probability assigned to it, instead of the assumptions and the things that we as Bayesians would like to treat as having probabilities. But again, if you think about the Orthodox kind of mindset, it's all about repeating that experiment over and over again, maybe with the apparatus or the setup of the experiment held constant, and the assertion is that you're going to get different data each time. Okay, so it's reasonable then to kind of think that it's the data that's randomly varying, and therefore the data that gets probability assigned to it instead of anything else. Okay, what that kind of means, or that kind of translates to, is that in the Orthodox techniques and methods, we're only ever really going to be asking questions about what other data could we have gotten, right? Or what is the probability that we got the particular data that we did get? Okay, so we're really just going to be interested in what Jaynes calls the pre-data questions. Okay, these are going to be the sole focus of statistics in this framework. And those questions will be things like what Jaynes says. Before we have actually conducted the experiment, what data would we expect to see? Would we expect, or what ranges of data would we associate to having high probability, or kind of what is the frequency of occurrence of data of one particular sort or another? So that's a pre-data question. Another question might be, let's say that if we use the data to do some estimation, so let's say we use it to estimate an unknown parameter. Okay, so we have some kind of defined procedure by which we turn the data into some parameter estimate for something we don't know. We might ask the question, how accurate do we expect that estimate to be, in the sense of how often do we think that it will be within some small range of the true value of that parameter. Okay, we're going to get to this in a minute or two. But that's, again, a kind of pre-data question of imagining doing the procedure over and over again with unknown data. And a similar kind of version of that, or just a twist on that, would be, let's say we use the data to test a hypothesis. Okay, let's just call that hypothesis H0. The question might be, if it is the case that H0 is true, okay, how likely is it that the data will confirm that the hypothesis is true, or lead us to accept the truth of the hypothesis? Okay, so again, a pre-data question where we imagine some procedure from which by which we're going to take the data and use it to test a hypothesis and either accept it or reject it. And so the pre-data question would be, all right, do that over and over again. How often is it that we're likely to get that data that supports that hypothesis, assuming that it's actually true? Okay, you could ask other questions like, how likely would we reject it if it's false, et cetera, et cetera. Okay, but these are the kinds of questions that basically Orthodox statistics is obsessed with. And the reason for that is that only the data is allowed to be random. So any probability question we want to ask has to do with, it must have to do with probabilities about the data and things that we can derive from the data. Okay, but all of that has to be kind of settled on ahead of time. All right, so this is what Jaynes calls the pre-data questions. Okay, so let's see how that plays out, maybe in one or two examples. Well, in particular, what we're gonna want, or what we're gonna be most interested in, I should say, from an experiment, is any kind of quantity that we can derive from the experiment. Okay, so what we really kind of care about in this Orthodox world are these things called random variables. Okay, which are any quantity derived from the data. So in the example we had before with flipping two coins, that might be something like you define the quantity number of heads, right, in the outcome of flipping this pair of coins. And so that number just is a summary of the data in some way, okay, in a single number. And so the whole question is going to be about, what can we say about the sampling distribution of this random variable, okay, these random variables. Okay, so being a quantity that depends on the data, since the data is random, this number is random, allowably in the Orthodox way. So what that means is that it has probabilities associated to it when you talk about its distribution and probabilities of getting it in a certain range or another. Okay. So if we want to do something like parameter estimation, okay, what we were just kind of talking about, what that is going to consist of is choosing a random variable as what's called an estimator of this unknown parameter. Okay, so we'll do an example in just a minute. But the idea is, all right, we can quantify the data in any kind of summary way that we want, and in any kind of summary statistic that we choose to calculate from it. And the question is, all right, maybe that data depends in some way on some parameter that is unknown to us, right? So what we're going to try to do is pick one of those functions of the data that should allow us to basically extract the value of that unknown parameter in some way. And basically what that's going to amount to is the claim that a good estimator is one where its distribution is kind of closely confined to this parameter value. Okay, so this is really the whole game of orthodox statistics, is picking estimators or test statistics that, when you look at their sampling distributions, are kind of narrowly confined in a small neighborhood of whatever parameter it is that you are interested in. And then you're basically going to just say, okay, we'll use this test statistic as a proxy for that unknown parameter. Okay, so let's do an example and maybe make this a little more clear. Okay. Okay, so the example would be, let's just do the urn drawing example that we had before. Okay, urn drawing with an unknown proportion of black balls in the urn, and let's call that proportion theta. Okay, so imagine we've got this urn, okay, some urn over here, and it's got some large number of, say, black and white balls in it, and some fraction of them are black, but we don't know what that fraction is, so we'll just call that fraction theta. Okay. Our data in the experiment, as we had it before, is going to be some number, which is going to be n, let's say little b, black balls in a sample of little n. Okay, so we imagine there's a very large number of balls in the urn. We pull out some small sample relative to the total. Sample without replacement, we're going to ignore that in a minute. And we assume that the data that we got was that NB of them were black balls, and we took out a sample of little n total. Okay, so the question is, how do we get from this data to an estimate of the value of theta? And in the orthodox framework, that means we have to define things in the kind of pre-data way. So we have to think first of what our estimator or our statistic would be that we think might be narrowly confined to a small neighborhood around the true value of theta. Okay. In this case, I think it's relatively clear what our estimator is going to be, and that is that we're interested in the kind of proportion of black balls in the urn total, and we did a sample of it, so it's reasonable to think, all right, let's just take the ratio in our sample as our estimator of this value theta. Okay, so the claim is if this sample is relatively large, or if we can kind of write down probabilities of this f, we should get things that are kind of tightly distributed around the true value theta. And the thing to notice here is that f, this number, is a random variable. It's a summary number of the data, basically something we compute from the data, which is random in the orthodox description, meaning that if we do the sample over and over again, we're going to get different values of f. We're going to have different numbers of black balls in the sample. So when we compute this ratio, we're going to get a different number each time. So we're allowed to talk about probabilities of this f living in different ranges. Okay. Now some nice properties of this and things that are actually good about this estimator kind of come out if we start writing down actually what its sampling distribution is. Okay, so let's think about the probability of, first of all, what is this probability of getting NB black balls? And imagine that we can condition on some value of theta, even though we don't know what it is, but we're just going to imagine that it is some fixed parameter, and we're going to condition on it. Okay, so we saw this before, that the probability of getting this kind of number of black balls out of a sample of n, given some proportion in the urn, we can write out in terms of the binomial distribution. It's going to be something like n choose nb, theta to the nb times 1 minus theta to the n minus nb. Okay, now there's a little bit of a fudge here because we said we're sampling without replacement. This is the formula for sampling with replacement, but we'll just say that little n is very small relative to the huge population of balls in the urn, so we're approximating it as the binomial distribution. And here we're not worried about the sequence that the balls came out in terms of, in which order they were white and black, so we're just saying the probability of getting that number of black balls. Assuming that the proportion was theta, we can write down in terms of the binomial distribution with theta as the kind of success probability. Okay, so far so good. What this means for the distribution of f is actually that it has exactly the same distribution. It's just that we, instead of talking about this number as a function of nb, we're going to concentrate it or sort of scale it down to the kind of possible proportions, which would be like 1 over n, 2 over n, etc. up to 1. Okay, so we basically just take this binomial distribution number, and then we take it as a proportion, and all it does is scrunch down the distributions that it's now concentrated on these ratio possibilities, which are from 0 to 1. Okay, and those are the allowable values for f, the way we've defined it. Okay, great. So we kind of know everything there is to know about this sampling distribution of f. Now, one of the things that we haven't talked about yet, and we sort of skipped over in the book, but another thing that makes this a nice kind of estimator for theta is that if we think about the average of this random quantity nb, okay, again, it has a probability distribution that has theta in it as an unknown parameter, but we're just kind of thinking about that as fixed. If we then kind of take the weighted average over this distribution from 0 to little n, the average of that distribution is actually theta times n. Okay, so that's just a property of the binomial distribution. And so if we then scale that thing down and talk about the distribution of f, we're going to have that the average of the value f is this number theta. Okay, the average of our summary statistic over its distribution is actually just equal to whatever this unknown parameter value is. Okay, and the way that you might write that mathematically is in terms of the expected value operator, and you'd say expected value of f conditional on theta, again, assuming that it's kind of fixed, although it's unknown to us, is itself the number theta. Okay. Now, when that happens, what we say is that this estimator is what's called unbiased. Okay, and unbiased means that the average of its sampling distribution conditional on any value for the unknown parameter is just the parameter value. So in, let's say, a large number of trials, if you repeated this over and over again and you looked at your f value each time, and then you kind of averaged those up, there's some law of large numbers averaging argument that would get you to say that that average should actually converge to the value theta, whatever it is. Okay, so when that happens, we call this an unbiased estimator of whatever parameters we're interested in. And we can just think of this as being kind of a nice property that estimators might have, okay, that they average out to being the real value if we do the experiment many times. Okay, but actually we can say somewhat more than that. If we think a little bit more about this distribution of this quantity f. Okay, so we talked about this a little bit before with the sampling with and without replacement. But basically the question is, how likely or how much would we expect f, how much does f deviate, let's say, from this parameter value theta on average, or with what probabilities? Okay, so for that, we can either write everything in terms of this binomial distribution, or we can just kind of make the observation that the distribution of this number f is about equal to a normal distribution with the mean that we said already, which is theta, and some standard deviation, sigma, and we'll write the normal distribution this way. Okay, so again, we skipped over the parts in the book where we talk about the normal distribution. This notation here just means the bell curve distribution with this center point, theta, and a spread, a standard deviation that's called sigma. We write sigma squared for some obscure reason. But that just basically says how much the bell curve is distributed around that. And in fact, we can say that this sigma is a number that is proportional to 1 over the square root of the sample size. Okay, and, technically it depends on theta. We're just going to ignore that for the time being. We're going to assume theta is somewhere in the range of, the middle of the range of 0 and 1. And the standard deviation of this normal distribution is going to depend in some way on the sample size, where it goes by 1 over the square root of n. Okay, so if we kind of draw that as a picture, it might look like this. Okay, so we'll have theta being some value just in the middle here, somewhere between 0 and 1. The distribution of f then will have its peak kind of around theta. So this is distribution of f. And the spread of that distribution, okay, however we really want to define it, is some number sigma, where sigma is proportional to 1 over the square root of n. Okay. Great. So if we make that approximation, now we can say a lot about probabilities of getting f in various ranges of this distribution, and we can ask things like, what is the probability that f deviates from theta by some largest number? And we'll be able to make statements like the probability, let's say that the absolute value of f minus theta is greater than some number, let's call it epsilon. That probability is kind of small. Okay, depending on what we mean by small and depending on what epsilon we choose, when this n value gets to be large. Okay, so the larger the sample as we take, the more tightly concentrated this distribution becomes around theta, and so the smaller the probability is that f minus theta is any kind of largest number. And in fact, f and theta should be equal to each other to within some fairly high precision if we take a large enough data sample. Okay, so this is the sampling distribution of f, and this is basically the main object in all orthodox statistical calculations, the main kind of thing that we're interested in. Okay, now we can actually go just a bit further with that. Okay, this probability statement that we have here looks very suggestive, and is actually the kind of thing that, for us as Bayesians, we'd like to be able to say this has to do with probabilities of theta, right? But in the orthodox mind, we don't have probabilities of theta, because theta is not random, right? Theta is a fixed number, even though we don't know it, right? So basically, this is just a statement about how likely f is to be in some range around theta, right? If we repeat the experiment over and over again, but it kind of looks like suggestive. I mean, it's basically saying, all right, f and theta they're close together, so we should just use f and be happy with it, right? So we might just be tempted to kind of just stop there and say, all right, we're done. What we can do just to clarify that a little bit is to define a hypothesis, let's call it h0, that theta actually has a particular value. And I don't know, let's just say it's 0.5. Okay, it's the value we're interested in. right? So then the question is, all right, we know kind of conditional on this hypothesis what the sampling distribution of f is. What we're going to try to do is basically accept or reject this hypothesis based on the value we actually do observe. Okay, so what we're going to say is, let's define what's called a rejection region. Rejection region for the value f, which is some region where it has low probability. Okay, what do I mean by low? Conditional on this value h0. Okay, so the way that usually works is that we will say, all right, let's just assume that we have theta is 0.5, so we're assuming that this hypothesis is true. We'll define a region of the distribution where we're going to reject that hypothesis if we observe a value f in that region, and we'll do it in such a way that it's kind of low probability and it's extreme away from the value theta. Okay, so basically what we'll do is we'll set up some area of the tails of the distribution, maybe out here and out here. Okay, and we'll say, let's pick this value of the deviation, call it little z. So let's pick a value little z such that the probability of f deviating from this particular hypothetical value of theta by an amount greater than z, conditional on this hypothesis h0. Okay, so this is absolute value. This is the conditional bar. The probability of that conditional on h0 is some small number, and the number we usually take is 5%. Okay, 0.05. Okay, so we basically find this z such that the area in this tail region adds up to this small constant, and why we usually take 5% is for historical reasons. It's just kind of the standard practice. Okay, so this is called the significance of the hypothesis test we're doing. And what we can say is, all right, based on this binomial approximation, we can compute this value of z, right? So conditional on h0, f is a normally distributed variable with a particular standard deviation that actually has this as its mean. So we look this up in a kind of table of the normal distribution, and we can find what percentile level gives us this 5% tail area. Okay, if it happens then that that we get this this deviation greater than this kind of cutoff value, then we're going to reject the hypothesis h0 kind of at the 5% level. Okay, so that's a phrase that you'll hear very commonly in the world of Orthodox statistics, where we say we reject some hypothesis at a particular significance level, and the significance level comes from this definition of this rejection region, which is how far out in the tails do we have to get before we say, all right, enough is enough, theta is not 0.5. And again, the idea is here that we should only be rejecting this hypothesis at this level if this very kind of unlikely event has occurred. And if the hypothesis is true, we know what that probability is. Okay, so the whole kind of logic here is that the significance level is the probability that we would reject the null hypothesis, assuming that it were actually true. Okay, if it is not the case, let's just say if otherwise, then we will accept the hypothesis. Okay, or we will fail to reject it at this 5% level. Okay, when we do reject it, usually what we do is say, okay, maybe we got some value f that was out here in the tail region. We'll actually look at, all right, how much area was there kind of more extreme than f or minus f, okay, if we're doing a two-tailed test. And we'll call that the p-value. Okay, I didn't mention here. P-value is the kind of remaining tail area. And we might say things like, p is less than 0.05. Okay, so again, a statement that you're going to see a lot if someone claims to have a statistically significant result is that they got a p-value less than this 0.05. It just means that they got a value in their kind of 5% rejection region. Okay, if we didn't, do that, let's say that we got a value f that was closer to this hypothetical theta value that we were testing, we would say that we accept h0, at the same level. Okay, we do not reject it at the 5% level. Basically, we go back to the drawing board, we don't publish our result, and we try to set up the experiment again and get a significant result. Okay, so in Orthodox statistical practice, we're only really kind of trying to find these places where there's a real effect, and those are what we can go to press with. Okay. So then that's basically the logic of the hypothesis test. What we could do actually is imagine then repeating it over and over again with different chosen values of this theta. Okay, so again, here it's like we imagine that we did not reject the hypothesis that theta was 0.05 because we got a value of f that was fairly close to 0.05. So now the question might be, okay, for what other values of theta would we accept the hypothesis? The hypothesis of that value being theta. Okay, maybe we should say for what values of theta naught would we accept the hypothesis that this parameter is theta naught. All right, so basically what that amounts to in this very kind of simple setup where theta is just the mean of the distribution is we might say, okay, we didn't reject the hypothesis here because f fell in the kind of bulk of the distribution, assuming that it was centered around 0.5. So now imagine shifting that distribution up and down and finding all of the values of theta for which we would not reject given this particular realized value of f. And what that would kind of consist of is kind of taking the distribution, sliding it down until f got to the very border of that rejection region, on one side, and then sliding it up the other way until it got to the border of the rejection region on the other side. And when we did that, if we did that over and over again, we might come up with an interval assignment. Okay, so we get basically some range of thetas, shown by this blue interval. Okay, and those would be the values for which we would not reject the null hypothesis that theta had that value, and this is what's called the confidence interval. Okay, so again, having chosen this 5% significance level, if we did this over and over again, or imagined doing it over and over again, and asking the question for what values of theta would we not reject this hypothesis, that becomes what's called the confidence interval assignment for theta, and it just means basically, all right, we think f is the right value, but what kind of uncertainty do we place around that? Or what interval would we kind of say is a reasonable guess for where the parameter lives? And you'll see things like the claim that, okay, if you do this over and over again for different values of f, the confidence interval should contain the true value of theta about 95% of the time. Okay, so again, a kind of predata question of running the procedure over and over again. Okay, so that's hypothesis testing, confidence interval calculation in the Orthodox framework. Okay. So really then, that's kind of the logic for all statistical inference in this Orthodox world. Okay, so this example is fairly simple where we have a simple kind of normal sampling distribution and everything's kind of well defined, but you can basically take this as a template for all other possible statistical questions that you might want to ask, or all other parameters that you might want to assign values to or test hypotheses on or define confidence intervals for. Okay, so again, the kind of procedure for all of this, I'll just right over here, is going to be something like first define a model, okay, with some unknown parameter and some sampling distribution of the data, okay, conditional on that parameter value or on that hypothesis, maybe. Okay, whatever it is you're interested in testing. Okay, choose some estimator, okay, or test statistic or whatever it is, and compute its sampling distribution under this model. Okay, so whatever summary quantity we want of the data, we can kind of write out probabilities of its sampling distribution conditional on the hypothesis being true. Okay, then maybe define a rejection region or acceptance region or significance level or whatever it is you want to do, rejection region, and then use that to test the hypothesis, H0, or calculate a confidence interval or whatever it is. Okay, so really the kind of name of the game in Orthodox statistics is going to be in here, right? So what we're going to have to do is think of what is the kind of right test statistic that we might compute as a function of our data to summarize it in such a way that we can calculate its sampling distribution. Okay, could be potentially kind of a hard problem. And from the sampling distribution, we have to then think about what is our kind of rejection criteria for the hypothesis and what region of that test statistic would cause us to reject or accept this hypothesis. Then maybe we play the game over and over again, come up with a confidence interval, or et cetera, et cetera. Okay, so if you read a standard statistical textbook, this is where the great bulk of the material is going to lie. It's going to be in defining different possible test statistics for different kinds of estimation problems. Okay, so the one we mentioned here is a fairly simple one where we're estimating the mean of a binary variable that's either 1 or 0. But it could be, let's say that we want to know things like the average of some quantity over a population where the quantity is varying. So maybe the average height of people in a population based on a survey sample. Or we might want more complicated things. So we might want to know things like the correlation between two numbers, like the correlation between cholesterol levels and incidence of heart disease, or things like that. Or the effect size that some drug has on some of these diseases or the rates of these diseases. And we can't look at the whole population simultaneously, so our data is always going to maybe be some survey sample, some randomly chosen sample of people in the population from which we're going to test hypotheses about the distribution of that quantity or that correlation number or whatever it is. Okay, this could even go much further, and we could be asking questions like, is there a difference in the means between two subpopulations of our greater population, or is a certain quantity distributed in a certain way that we think it is, right? So maybe in the population we think it's got a normal distribution, and we want to test that based on a sample. Or are two things independent, or so on and so forth. Okay, so basically any kind of question we might want to ask is usually going to be framed in terms of populations and quantities that are varying over that population, and the experiment is going to be conducting a sample, and the big question is going to be, okay, how do we summarize the results in that sample to get these test statistics or estimators in such a way that we can compute their sampling distributions. Okay, so you're going to see a lot of fancy kind of distributions and tables of their percentiles and places where the rejection region is for that whatever that hypothesis is. And this is really what most of statistics is in the kind of orthodox presentation. Okay, so Jaynes compares this in some way to the relationship between a patient and a doctor, right? So if you're some scientist and you're trying to do this kind of analysis on your problem of interest, right, you may either kind of look that procedure up in some standard recipe book like R.A. Fisher's methods book, or if it's a really complex problem and you want to make sure that you do it right, you might consult with a professional statistician and say, okay, what's the right test statistic for this problem I'm interested in, and how should I set my rejection criteria, and make sure that when I publish, I've done kind of all the necessary legwork to design the experiment correctly and design the statistics correctly. And it's going to be different for each problem. Okay, so it's like a kind of doctor-patient relationship where you come in with some ailment and the doctor says, okay, for your set of symptoms, I would say that this treatment is the right one. And there's no kind of unifying logic for which treatment goes with which condition. It's just basically case-by-case basis and based on empirical results from having done this before. And really, I think if you want to think about what Jaynes is trying to accomplish with this book and the whole kind of philosophy of developing the book the way he did, it's to take the power away from the professional statistician and put it into the hands of the scientist. Right? So his claim is going to be that once we've torn this all down and replaced it with our kind of logically consistent framework that is universally applicable to all problems, right? The only thing you're going to need to think about is, all right, the particulars of my problem, but the logic and the thought process are going to be the same for everyone. So once you learn those basic principles, you're just basically going to be able to do that procedure yourself as the scientist, and you don't need some statistician to tell you this is the right statistic for your problem. Okay, so I think he even kind of hints at the suggestion that it was the threat to this kind of power structure of the statistician as the final arbiter of what methods were right for each of these scientific problems that made this such a destabilizing idea and made them so resistant to the Bayesian methods that we're going to try to replace them with. Okay, so we'll get to that a bit more, but that's just kind of the sociology, if you like, of maybe what's going on here. So as I said, next time what we'll do is criticize this pretty harshly and take this apart and show where this procedure is going to give us absurd or illogical results. Given where we are in the book and what we've seen so far as the kind of Bayesian version of this, parameter estimation or hypothesis testing, I think you can anticipate where that critique is going to come from. Okay, so we're going to basically say things like, in this framework, we rejected this hypothesis because we got some data that's very improbable. But we know that improbable data is not necessarily evidence for or against a hypothesis unless we have some specified alternative. Okay, so where we're going to attack this is basically in the failure to specify an alternative hypothesis and talk about what its sampling probabilities would be. And therefore, the fact that this is improbable data may matter or may not matter. The other places we're going to attack this are basically all in these assignments of probabilities to data as being the only thing that matters. Okay, so really we know as Bayesians what we'd like to do is not ask the question of what other data could we have gotten in the experiment but we did not get. The questions we'd like to ask are the post-data questions of, all right, conditional on what we did observe, what probabilities do we assign to the hypotheses of the things that we're actually interested in. Okay, so that's going to be our inferential strategy. And since we can talk about probabilities of a hypothesis or probabilities of a fixed parameter, having some value just because we don't know it, we're able to do that in a logically consistent way. Okay, so I think we can already kind of guess at where this is going to go wrong. We'll get into that next time. For the rest of this video, I think what will be useful is to just see where this might go right and actually how this might give you some reasonable values, or at least overlap in some way with the framework that we think is the right one. Okay, so what's that going to look like? Well, we've done this already a little bit, and we actually kind of talked about this problem some with the Bayesian inference problem of assigning a posterior probability distribution to a proportion of bad widgets or whatever it was. Okay, so let's just kind of repeat some of that and play that out and see how we would attack this problem kind of the right way. All right, so we actually would agree with a lot of this argument up to the sampling distribution of f. Okay, so we would certainly agree with the statement that the probability of getting a certain realized fraction of black balls in our sample, assuming that, or conditioning on the value in the urn, the proportion in the urn being theta, and let's just throw in background assumptions here because we like to track our background assumptions, we would agree that this thing has a binomial distribution approximately, and we would actually make the same approximation as the orthodoxians would, and say that that's going to be about a normal distribution where sigma is something proportional to 1 over square root of n. Okay, again, it technically depends on theta, but we're going to ignore that for the time being. Okay, so we're totally on board with all of this sampling distribution stuff. This p here, we didn't talk about this too technically, but this is the probability density function. Okay, so we mentioned this a little bit a few videos ago, but basically this is going to be the probability of getting a value in some small interval, okay, just as a function of that constant f. If we then imagine doing a hypothesis test and assigning a posterior probability density function for the unknown parameter that we care about, theta, how would that look? Well, basically we would say our posterior probability for theta, given our data variable f, is going to be like its prior times some ratio where the ratio is this particular sampling probability divided by its total probability. Okay, so we won't worry about this too much. This is just a sort of normalizing constant to make this thing integrate up to 1. But the important thing is here that we have our data likelihood, our data probability, just as before, but now we also have our prior assignment for the parameter theta, which just comes from our background assumptions, okay, before having observed the data. Okay, so again, we haven't done exactly this with density functions, but given the kind of Bayesian experience we have thus far, I think you'll probably believe that this is going to be the procedure for computing now our posterior probability density function assignment for this parameter theta based on what we observe. Okay, so now here comes really the key point, which is that if it is the case that this prior assignment density function for theta is uniform, okay, meaning that it is just a constant value, right? What are we going to get? Well, this is basically going to drop out. Okay, this is some normalizing constant, doesn't depend on theta. This number here we know is the data likelihood. Okay, so let me just write this up here. I didn't write it. So the density function for the normal distribution is proportional to the exponential of the difference f minus theta squared divided by 2 sigma squared. Okay, that's just the form of the normal distribution with some constant in front of it. So what we'll get is the same thing, right? So we've got a constant here, we've got a constant here, don't depend on theta. The only thing that's left that depends on theta is here, which is just the same function. Okay, so we're going to get a posterior probability assignment that is proportional to this likelihood function. Okay, it's proportional to e to the minus f minus theta squared over 2 sigma squared. Okay, so far so good. Maybe it looks a little bit strange. And now here's the real kicker, right? This function, right, now we're thinking of it as a function of theta, but this function is symmetric in f and theta, right? So this actually is equal to e to the minus theta minus f squared. There's a minus here. F squared divided by 2 sigma squared. Okay, So what it means for this posterior probability assignment to be proportional to this quantity, now thinking of it as a function of theta, is that this is the normal distribution, right, for theta with a mean that's equal to f. Okay? So hopefully you see that. And this is pretty amazing property. Okay, so what that means is that, again, we're thinking about this posterior probability assignment for theta, right, posterior to having observed f, and what we get in the end is that it's a normal distribution with a mean given by f. So this is our kind of state of knowledge about this unknown parameter theta is a normally distributed variable with a centered around the peak value at the value we did observe, which is f. Okay, so if we were to draw as Bayesians the same kind of picture we had here, okay, same kind of picture we had before in the orthodox framework, what we would say is, okay, here's our value of f that we did observe. We have a bell curve centered around f. Okay, not very well drawn, but you get the idea. It has the same kind of width as the bell curve we had before, and this is our posterior assignment for the value theta. Okay, so here, yeah, sigma is again proportional to 1 over the square root of n, where n is the size of the sample. Okay, so if we look carefully at these two graphs, we should see basically that they are saying the same thing. Right? So the orthodoxian argument got us to this sampling distribution for f, which is kind of its frequencies over many possible trials, assuming that the value theta, put theta back in here, value theta was fixed and unknown. So f varies around theta. Our kind of argument is that our posterior probability assignment for theta is a normal distribution that varies around f, but these look so similar to each other that it's not surprising that we're going to get the same numerical answers for whichever way we now want to interpret these distributions. So if we do kind of a null hypothesis significance test in the orthodox framework, or just a parameter estimate from our posterior probability distribution, or a hypothesis test based on this posterior, we're going to get the same answers. Okay, so this correspondence is really, I think, in the story that Jaynes tells, this is the reason why orthodox statistics got off the rails, and why they were led to conclude that their methods were right, despite the fact that they are clearly illogical. Okay, and the reason for that is that, as we mentioned, Fisher and others were really interested in problems of biology, okay, where this might be actually kind of a reasonable setup. Okay, so remember, the kind of key ingredients of this were, first of all, that we had a uniform prior for our unknown parameter. A uniform prior, and we had a nice sampling distribution, which was this Gaussian function or normal distribution. Okay, and that might be applicable to more distributions. But when that setup occurs, we should get, or we expect to get now, a correspondence between the Bayesian and the orthodox method. Okay, so the suggestion is that because Fisher and others were thinking about problems where this is actually kind of a reasonable approximation or assessment of their problem, namely problems in biology where it's like, okay, you've got something that occurs at some proportion in the population, but you don't know what that proportion is, and you make no kind of really kind of cogent prior assumptions on it distributionally, and when you do your survey sample, it's reasonable to think that you get normally distributed data, or to assign a normal distribution to the sampling distribution. When those things happen, this procedure gets you to the same place that a Bayesian procedure would have gotten you to. Okay, so Jeffries is able to basically pick up that same problem and get to the same answer, even though the approaches are completely different from each other. Okay, where we expect it to break down is where one of these things might not be true. Okay, so in, say, Harold Jeffrey's problems of geophysics, where you have a lot of cogent prior information that you're bringing to the problem, equations of the relationships between different variables and kind of all of the assumptions you have about the values that parameters might have, and maybe more complex kinds of sampling problems where the experiment is not just drawing balls from an urn or drawing people from a population, but it's something like measuring some quantity or putting it into an equation and looking at what value you get out of it. Anything that's more complicated than this kind of ignorance prior and normal sampling distribution, we'd expect to see the Bayesian methods giving you different results from the orthodox ones, and that's what we're going to get into next time.